Okay, come. Okay, let's start for today. I just need you guys to take out your chem bonding notes. Right. Okay, to start things off, right? Okay, let me just preface this first. Okay, this chapter, I will only go over 4 lessons. Okay, because we can't afford to go over this in 5 lessons each. Okay, again, depends on. Okay, so see how our pace goes first. Okay, because for most of you guys, I've already gone through dot and cross diagrams with all of you. Okay, so I want to split the chapter first. Okay, because generally, right, we allocate 5 lessons to this because I need you all to also split the topic into 5 portions. Okay, because if you don't split it into a couple of portions, right, you're gonna end up having a lot of concepts gelled together, and that's when you get a lot of things wrong. Okay, that's why a lot of people suffer in this chapter. Okay, because they don't know how to split it themselves. Okay, so today, right, our main and sole purpose is to go over this thing called structure and bonding. So again, right, just copy this down first because that's my way of splitting this chapter for everyone. All right. So when you study yourself, you may not want. Okay, let's say you don't want to follow my way, right? Okay, it's fine now. Okay, but then this is my preferred method. Okay. So today we're gonna focus on the first one. Now the second lesson usually, right, I just talk about dot and cross diagrams. Okay, but we have already covered a little bit of that. Usually, in the next lesson, I will cover VSEPR theory. Okay, this is like the main idea. Okay. Then the third portion of the chapter, we will dive into this thing called electronegativity. Rather new concept that I've already briefly introduced to you guys. Okay, but on top of that, right, there's also this thing called intermediate bonding. Okay. Now, intermediate bonding is a rather interesting idea. Okay, and even though it has the word bonding inside, okay, I'm not going to go over that today because it's a rather advanced idea. Okay. Moving on to the 4th and 5th portions, right? Okay, we will discuss this thing called intermolecular forces of attractions. Arguably the most important segment in this entire chapter. Because everything else from now on, right, all the chapters, right, will always have some sort of connection towards intermolecular forces. So for the 4th lesson, right, we will discuss the types of intermolecular forces. And then basically the last portion is to apply these intermolecular forces. Okay, when it comes to applications, right, okay, we only have a very limited scope. Okay, so in our syllabus, we deal with melting, boiling points, and the more important one, right, is actually solubility. Okay, all these things are very far from where we are currently. Okay, other people, my other students already covered, finished this entire chapter. Okay, so we no choice have to shorten it to 4 lessons. Okay, if not, we will never catch up. Okay, so when you study this chapter, you need to look at it this way. Okay, for a more cohesive way of understanding this entire thing. Okay, it's all linked together. There's a reason why it is in this order as well. Okay, but anyways, today, right, when we discuss structure and bonding, you have to split it into even more smaller points, okay, to make it more manageable. For every type of structure, we will have to answer 3 questions today. Okay, structure, bonding, and the most important one is the factors affecting strength. Generally, guys, structure and bonding, you guys have already learned in secondary school, right? Okay, of course, there's a bit of tweaks in JC. But today, your takeaway should be under here, factors affecting strength. Now, let me just give you guys an introduction. You already know metallic bonds, ionic bonds, and covalent bonds. Okay, those are very, very straightforward. Okay, but for today, covalent bonds will be a little bit more challenging because it has the most new things. So without further ado, I want you guys to take a look at the first page. First couple of pages, okay, we are going to look at metallic bonding. Right? So to answer the 3 questions very succinctly, right? Let's just look at it this way. When we come to look at metals, okay, our main idea, the structure, you must take note. You cannot just say giant metallic structure anymore. We try to use the appropriate words over here. Okay, when it comes to structure, we are looking at giant metallic lattice. So nowadays, right, I think last time they can still allow you guys to use the word structure. Formally speaking, we try to use the word lattice from now on. Okay? Now, what I'm more concerned with is the bonding. Now, guys, take a look at the bonding, right? I want you all to take note. All types of bonding, you can write somewhere else. All types of bonds are electrostatic forces of attraction. Now take note, you all have seen this idea before, electrostatic forces. But in JC, right, you won't have time to write this phrase all the time. Okay, really no time in exam. And because of that, luckily for us, we are able to shorten our answer to make it a bit more concise. You can simply just tell me metallic bonds. Again, it is a type of electrostatic force of attraction. So just tell me metallic bonds, but this is still not enough. You must specify between what. And again, if you remember your secondary school stuff, none of this seems very new. Okay, it's between the metal cations and the sea of delocalized valence electrons. Now, in the notes, there's one word that's missing, which is the word valence. And I need you guys to really highlight this and put it into your definition. Now, not to say that the notes is so-called wrong, but nowadays they are getting more strict with this word valence already. I think back during my time, right, that it doesn't really matter, like they didn't really look out for it. But nowadays, they're super strict when it comes to the word valence. They've tested this in last year's paper, and then half the cohort basically picked the wrong answer, which was very bad. So to understand this in more detail, okay, I'm pretty sure you all can kind of remember what delocalized means, right? Can someone tell me what delocalized means in like simple terms? Any idea? Okay, like free to move, right? In other words, they move freely. Move freely within what? You have to understand it moves freely within the entire lattice structure. Okay, so visualize a bit first. What does valence electrons here? What does it actually say? Like for example, guys, if you look at magnesium, can someone tell me how many valence this guy has? 2. Okay, good. Now, meaning to say, for every magnesium cation, right, only 2 valence electrons will end up moving throughout the entire structure. The magnesium has a total of 12 electrons, right? Okay, the other 10 electrons are still fixed within the cation. Okay, so you cannot say that 12 electrons are delocalizing across the entire lattice. That's a bit too much. Now that I've told you guys this idea, right? This will help us answer the next page question. Okay, so before you flip over to the next page, just take a look at the diagram printed at the bottom of the first page. That is roughly how a metallic structure looks like. So now I need you all to turn over, right? And try to do something similar for aluminium. It should be something quite menial, okay? So we get this over and done with. Okay. Right, so they're asking for aluminium. The diagram is similar to what we just saw. Okay. Okay, so I see some of you guys have some very interesting variations, right? Okay, but from what I've seen, most of you guys have something similar to the previous page. In fact, I think exactly the same. Okay, so guys, I want to make a few comments. Okay, currently I don't think anyone has gotten the structure yet. Guys, this is aluminium, right? Most of every one of you guys here have only placed a +1 charge. Is that correct? Okay, I want you all to realize aluminium can form which metal cation? Al. What's the cation? 3+. Okay, so you have to contextualize things. For magnesium, it has to be +2. In this case, it has to be +3. Okay, so here is the 3+ cation. I'm just going to draw a handful of them. Okay, I see some of you guys draw a lot, right? Which is not wrong, but will backfire in a bit. Guys, what else do I need to draw in my diagram? What else? Okay, electrons, right? Okay, so they say metal cations have delocalized electrons, valence electrons. Does it matter how many electrons I draw? Or does it matter I can just whack? Okay, can I put like 1 electron here? Okay, what is there an exact number of electrons that I must put if my diagram looks like this? Can someone tell me? Why 12? Okay, good, correct. So guys, you have to understand every cation must be accompanied by 3 valence electrons because it makes sense. And again, why does the number matter? Because I hope you all understand that metals at the end of the day are neutral. They have no charge, meaning to say that the entire lattice, right, must have a neutral charge. The positive and negative charges must cancel each other out. So meaning to say you can't even draw 10 electrons, that's wrong. So in the exam, they will count the number of electrons that you all draw. And try not to draw too many, because I see some of you guys fill up the entire box, right? Okay, if you draw too many, you end up having to draw like 28 electrons or some shit. Okay, that's too much. So in the first few lecture tests, right, you might expect to see some questions like this regarding chem bonding. But eventually you stop to see these questions being tested because they don't want to count so many people's like freaking electrons. Okay, but just pay attention now. This one really helps you understand. These electrons are free to move around the lattice. Okay, and need to count exactly 12. All good so far. Okay, with that said, I just want to move on to the more important parts already. Okay, magnesium 2 plus, you can draw a total of 8 valence electrons if you draw 2, 4, 6, 8 like this. Okay, so that's pretty much it. Okay, and alright, guys, the next part is what I'm concerned with. Okay, we are discussing now the factors affecting the strength. Okay, kind of ignore the notes for a moment because the notes show 2 bullet points, right? But just look at the board. Right, I'm going to introduce a new idea to you guys called charge density. Now, I'm not going to just tell you what it means. Okay, we try to understand what this actually entails. Okay, guys, you all know what density is? Like, what is it? Okay, it's mass over volume, right? Okay, to put it simply, it's the amount of matter that's concentrated within a small amount of space, right? Okay, so it's the same idea, but now we look at charge density. So do you all agree? Charge density is basically how much charge is within a fixed amount of space, right? But let's contextualize this even further. Instead of matter, we use charge. And instead of space, what do we actually refer to? Guys, the charge is concentrated within what? Any idea? Okay, you all think about it. An ion contains a charge. So the charge is within its what? Not just the nucleus, but the radius of the ion. Does that make sense? Okay, the charge is not just within the nucleus for the cation. Okay, in this case, we are looking at basically the ionic radius. How much the charge is dissipated across its space, the ionic radius. Can you see that? So guys, I want you to think about it logically. If my charge is higher, what happens to my charge density? Will it be higher or lower? Also higher, right? Now, if my amount of space increases, then what happens to my charge density? Lower, right? It's the same idea as the normal usual density formula. Okay, it's like over here, there's only 4 of us in this big classroom. It's not very dense. But imagine like just now, right, that class was 12 people, that one's very dense, right? Okay, you want to understand this idea. So, but anyways, okay, go write down this relationship. Charge density is proportional to charge, but inversely proportional to your ionic radius, Q over R. Okay, this is oddly similar to what we learned in atomic structure. Atomic structure put here Q over M. But no, don't get it confused. A lot of people get it confused. Then suddenly tell me one mess. Okay, no, I cannot. Okay, can? Now, the next thing that I need to tell you all is this, before I let you all do a random question yourself. Okay, charge density, I'll take note, is a direct measure, keyword direct, okay, direct measure of metallic bond strength. So let me just ask you all, if the charge density of a cation is higher, the metallic bond strength will be higher or lower? If charge density is higher, metallic bond strength is also higher, because I already told you guys it's a direct measure of metallic bond strength. And with that information now given to you guys, I want you all to try the question on the next page. So this is the question here. They're asking you guys to explain why the melting point of magnesium is higher than the melting point of sodium. Now, this kind of questions will come out every single time. And I'm very particular over the wording. So I want you guys to try it yourself first. Then I'll look at each and every one of your responses. Then later I'll tell you what's needed and what's not. Okay? Okay, go and try this. Whatever you think that's important, you're going to write your answer first. Okay, you might want to write in pencil because your answer may not be perfect yet. Okay, then later we write down the second round of answer, which is a lot more polished. Okay. Okay, so maybe like another minute, then I'll talk about the full answer. Okay, because right now you guys don't know what's the actual criteria, right, for what is required in your answer yet. Okay, so let's polish things up a little bit. It's proportional to two things, right? Not just one. So to ionic radius. So try not to change this. Yeah, it must stick. So roughly then cross there. Okay, anyways, we just take a look at the answer. Okay. Now let me just say some of the do's and don'ts. Okay, because I feel that this is a thing that you all learn from like O levels. The more you write, then it's like better. Okay, no. Okay, JC, the more you write, you're just gonna kill yourself because there's not enough time in the exam. So let me ask you all, okay, when you look at two things like that, I really need to start to see comparative words. So I think some of you all will tell me magnesium's charge is 2 plus, sodium charge is +1. That's all unnecessary. Just go straight into telling me that the charge is higher, something like that. So to start things off, guys, we have to discuss the idea of charge density. Because melting point is linked to bond strength, which is then linked to charge density, correct? Now remember, I see some of your answers, right? Okay, y'all didn't acknowledge some things. Now guys, there are two factors for you to acknowledge. First of all, magnesium's charge compared to sodium's charge, is it higher or lower? Obviously higher, right? Okay, so also take note, do not tell me magnesium's charge. In fact, it's Mg2+. Mg2 plus has a higher charge than sodium plus, right? Now we are discussing the anion, so don't go and tell me the metal. If you tell me magnesium has a higher charge, that's wrong already. Okay, so the subject of the question of your sentence must be correct also. But before that, guys, I see some of you all forget to talk about one thing. Where's your ionic radius? Okay, you need to discuss ionic radius as well. If you are having trouble determining your ionic radius, I suggest, okay, you all take out your data booklet now. Okay, there's this one page that's very useful. Okay, just flip a couple of pages in. There's this entire page, right? Okay, that's literally tells you guys all the atomic and ionic radii. See that? What page? Okay, I think based on whatever I print for you guys is page for 51, right? Okay, so I think some of your data booklets are a bit different. Okay, yeah, 51. So the next page. Yeah, 52. Okay, so guys, take a look. Here, right, you'll never go wrong. You just go and compare the ionic radius of magnesium 2 plus and sodium 2 plus. And what can you all see over here? Magnesium 2 plus is bigger or smaller? Smaller. Okay, so this one really cannot go wrong. Okay, it's a higher charge, but smaller ionic radius than Na plus. Okay, so you notice I already combined two sentences into one. I realize some of you guys will tell me it has a higher charge than Na plus. The Mg2 plus is a smaller. Okay, so you're repeating yourself. Don't waste time. So take a look at this. If it has a higher charge and smaller ionic radius, can I ask you all, the charge density has to be higher, right? They both complement each other. So go straight into it. Tell me, Mg2 plus, still talking about the ion, has a higher charge density than Na plus. Now then, guys, what is the next point? After telling me it's a higher charge density, what does this imply? What does it imply? You can see I already told you charge density can instantly link to metallic bond strength. Now you tell me magnesium has stronger metallic bonds than sodium. Notice how the subject of my question has now changed. Metallic bonds are referring to the metal itself. So now use Mg. They're very particular over this. It's not that I want to make your life difficult. Okay, they will find any fault in your answer. Okay, so magnesium has stronger metallic bonds. And what's the final keyword that I need to input here? Anytime you want to link to melting point. Melting point, you want to melt something, it requires what? Energy. Okay, so I need to see that if you have stronger metallic bonds, you tell me which requires more energy to overcome. Now, once again, guys, I see some of your answers. You could potentially get very, very long, okay, I want to keep your answers as concise as possible because you don't have time in exam. Okay, so in this case, I see some of you all will do this. Magnesium has stronger metallic bonds. Magnesium requires more energy to overcome the stronger metallic bonds. You're repeating yourself for no reason. Okay, so now I'm going to highlight all the keywords because keywords are what you should be looking at when you look back at this page again. Okay, you don't have time to look at the entire wall of text. Okay, so this is the most concise you can make your answer already. And I want you all to continue this for the future questions that I'm going to show you all in a bit. So far, any issues? I'm very particular over this because it's very keyword heavy. Okay, if you have no issues, you can just flip over to the next page. Okay, I don't want to spend too much time on the next page anyway. So I just tell you guys what's important, what's not. Okay, any issues? All good, huh? All right, on the next page is just properties of metals, which is not difficult and it's not going to be tested all that often. If it was tested, I'll give you guys boxes to write already, but it's not. Okay, so if you take a look at high melting point, I think that one everyone will know why, right? Conductor of electricity, that one's common sense also, everyone knows why, right? Okay, just to reiterate once again, in order to conduct electricity, anything must have what? No matter what kind of compound you are, to conduct electricity, you must have mobile what? Charge carriers, right? Charge carriers can come in the form of anything that contains charges. Like for example, here is electrons. Later for ionic compounds is ions. So it's all over there already. I really don't have to explain this. This one you all did it in O levels, right? Okay. Okay, perhaps the only thing that I want to explain a little bit, right, is the idea of malleability and ductility. Right? So I know there's a lot of words there, so just take a look at the board first. Metals are malleable. What does that mean in simple terms, right? Okay, malleable and ductile is the same thing as synonyms of each other. Okay, they can bend without breaking. In other words, metals you can apply force to it, right? And then the lattice will not die out. Okay, why is that so? Let me just give you guys a pictorial representation, right? Then we can move on from here. Okay, so you'll notice something. I imagine the lattice structure, right? It's made out of layers, like cake like that. Okay, but then here I'll just draw 2 layers. Okay, and in each layer, right, guys, remember what the bonding is like? Metal cations and delocalized electrons, right? So I'm going to draw the cations first. Let me just draw 3 up here. Now I want you all to tell me, right? The cations on the bottom layer, should it look like this also? Will it be directly beside the plus charges? Why no? Because if they are like that, they will repel, right? Okay, that is not ideal. So what's going to happen is they will just alternate to minimize that repulsions. Not to say that there's no more repulsions, it's just less. Repulsions are bad. Okay, so you want to try to minimize that. But can I tell you all? Now, right, I'm going to apply a force. And what's going to happen is this. If I apply a force to the bottom layer, now the bottom layer is going to shift to the left, right? And it's going to shift a bit. But when it shifts, right, what do you all notice about the plus charges? When it shifts, it will be now right beside the positive charges on top, right? Which is what do you think is going to happen now? Now that the plus charges are right beside each other, you expect them to repel. However, this does not happen. Reason is because there will be mini electrons in the middle preventing these repulsions, right? As mentioned, electrons here are delocalized. They can move freely, so they'll just move in between to prevent any repulsions. That's why metals, the integrity of the structure is not compromised. Everything is written over there already. So honestly, guys, here I would say because they don't test this pretty much at all, you can write anything that makes sense. Okay, there's no strict keywords. It's not like just now where I'm very particular. Okay, so whatever, we'll just move on. Okay, if you don't understand how this works, then I'll explain again. Okay, but let's just go on from here. All good so far? The next point is on alloys. I don't want to discuss this because once again, I never see this come out ever. Alloys are just a mixture of metals. That's it. Why do people create alloys? It's because alloys are harder than like the usual pure metals. Okay, the reason is all over there. Okay, you all can read yourself. Really not important. They don't test this. Okay, Ken? If they have no issues, right? I want to go. Okay, we start to get harder and harder. Okay, I want to now talk about ionic compounds. Okay, there's no need for me to discuss the basics. You all know what ionic compounds are. Whatever. Okay, this one really not important. But all we just need to know here is how to answer the structure and bonding part. Okay, so same thing as before. Structure here, don't tell me giant ionic lattice or ionic compound. Okay, no, must be giant ionic lattice, not structure. Okay. As for the word bonding, let me just help you guys make your life easier a bit. You can tell me electrostatic forces, but remember, over here you can shorten it to just tell me ionic bonds. But ionic bonds between what? Okay. Now the note is right there, oppositely charged ions. They're not wrong, but what the heck, man? Why waste so much time? Okay, so you can just tell me between the cations and the anions lah. Okay, isn't that faster? And furthermore, guys, in the exam, don't tell me cations and anions. You must tell me the actual cations and anions. But if they give you MgCl2, you must literally tell me Mg2 plus and Cl minus, even faster. Okay, don't write a generic response in the exam, because they will give you an actual compound. Okay, that's all I just want to say over here. It's really nothing much for me to mention. All good so far? Yeah, okay, all the details are there. Okay, but I want to go straight into the factors affecting strength. Okay, new idea here. Okay, guys. When it comes to ionic compounds, we are looking at this thing called lattice energy. Now, I just need you all to stare at that formula and just notice a few parallels with what we learned earlier. Okay, take note, this is a proportional sign. And don't worry, guys, there are 0 calculations in this chapter. So there's no need to convert this to the equal sign and do all that stuff. Okay, no need. Okay, so look at the formula. I want you all to notice a couple of things. Number one, you'll notice, right, that this is very similar to charge density. Okay, what's charge density again? Proportional to what? Charge over ionic radius. Okay, guys, cannot say atomic because charge only have ions. Okay, atoms no charge. Okay, that one must be careful. They'll mark you down. Okay, and you'll notice, right, lattice energy is literally charged over ionic radius 2 times. Then they just combine together. Okay, now why? It makes sense because I want you all to notice an ionic compound like NaCl contains the cation and the anion, right? So here it's just the charge density of the cation and charge density of the anion combined together. Does that make sense? Okay, it's not hard to memorize this. The only small little detail I need you to take note of is what? Is there something that you all notice here? Is there some sort of inconsistency? F, right? Okay, you all notice the top is a times. Okay, I just need you to highlight that just to make sure that you don't make mistakes. On the very next page, the question there is to ask you guys, what do you think is the significance of this times and the plus? Can someone make a guess? Yeah, I don't want to give you the answer here. Okay, the charges use the time sign. The ionic radii use the plus sign. What does this mean? Any idea? Okay, let me ask you all. Number one, which one bigger? Times or plus in math? Times is bigger, right? If it's bigger, that means what? The charges are more. What's the word for it? The more significant. Okay, I need you to take note of this. Because times is larger, right? Take note, charges are more significant than ionic radii. Okay, let me clarify. Because some of you all may be asking me, if it's more significant, then why do I give a shit about ionic radius? Okay, because that's not what I mean like on face value. What I'm trying to say is that it is more significant when there are conflicting scenarios. When there are conflicting factors, right, then you need to tell yourself that charges are more significant. I'll give you an example in a bit of what conflicting factors mean. Okay, this appears quite often, more often than you think. And if you don't acknowledge this, you will get marked down. Okay, so come, let's see. If the charge of an ionic compound is higher, the lattice energy will be higher or lower? Higher also. Okay, great. If the ionic radius is also higher, the lattice energy is what? Lower. Now what happens to the lattice energy? Is there any change? It looks like it's cancelling each other out, right? One up, one down. So you say the lattice energy stays the same. That's what most people will say, right? However, is it actually the same? Do you think they increase by the same extent? No, because who increases more? The charge. As already mentioned, because charges are more significant, right? The increase in lattice energy is a lot more significant than its decrease due to its ionic radius. So in this case, to put things very simply, whenever you have any conflicting factors, right, you will look at the charge. You look at the charge for the final say. It's like the idea of you arguing with your boss. At the end of the day, who's the final say? You can argue all you want, but your boss has the final say, right? It's the same idea over here. Okay, Ken? So, at the bottom of that page, there's plenty of space. I need you to write down this sample question. Okay, of course, you need to explain. Okay. NAF, Na2O, who has the higher melting point? Okay, go. Once again, I'll go and walk around, see what you have written down in your answers. I'm gonna draw a straight line. This question is not part of this here, so just write as extra. Okay, some of you guys who haven't really done atomic structure, if you haven't finished atomic structure as the chapter, right, you can't really predict who has the higher radius or smaller radius. Okay, but then never mind, because at least we have the data booklet to assure us of the answer. But those of you who have done atomic radius within the past week, right, atomic structure within the past week, you could be able to predict it. Okay. Do not submit because you can't perform calculations with this sign. Only if it's an equal sign it has some values. So again, there's no calculations needed. Here you just need to compare. So is it bigger or smaller? Yeah. Okay, so no subbing in of values, because you are not required to calculate anything. It's just tell me which one bigger, which one smaller. Yeah. Okay, just one more minute. As you all can already see, there's a lot more things to consider compared to just now, metallic structures, right? Okay, come. Gonna look at the answer now. Let me show you guys what's required. If you look at these two compounds, right? What's the very first thing that you should compare? What are we actually comparing? Are we comparing sodium plus? No, right? Both of them have the same cation. Meaning to say, you can ignore the left half, right, of this entire equation. Right? Okay, there's nothing for us over there. So let's just not care about it at all. However, we need to take a look at the anions. Because as you can clearly see, right, this question is asking us to compare between F minus and O2 minus. So I'm talking about this anion first. Don't talk about the overall compound yet. Now let's see, from O2 minus perspective, is its charge larger or smaller? Obviously larger, right? So O2 minus has a larger charge, but how about its ionic radius? Larger or smaller? Okay. If you look at the data booklet under the ionic radius, you all will see that O2 minus also has a higher ionic radius. Can see that? Now, higher the charge, lattice energy will be larger. Larger the ionic radius, lattice energy will be smaller. Can see that? So are we to say that they have the same lattice energy? No, so that's not possible. How do we answer this question now? Again, here when you have conflicting factors, it is important for us to bring this into our answer. So come, let's see. First, you tell me that O2 minus has a larger charge and larger ionic radius. No need to bring out any of the numbers or anything. Just tell me larger charge. All the comparative words, that's all you need. Okay. O2 minus has larger charge and larger ionic radius than F minus. Okay, then now you can basically link to your lattice energy. Okay, since charges are more significant, so you need to acknowledge this first. Okay, it's more significant than ionic radius. Okay, this is a disclaimer. Now that's more significant, you tell me that the lattice energy of Na2O is larger than that of NaF. So now you notice I'm not talking about the charge any longer. When I talk about lattice energy, I'm referring to the entire ionic compound. Okay? And as you guys can guess, what is lattice energy? Lattice energy is a direct measure of ionic bond strength. There's a lot of similarities. It's like how charge density is a direct measure of metallic bond strength. So all these are just fancy terms only. So now we can tell me if the lattice energy is higher, Na2O has stronger ionic bonds. Just go straight into it. Don't need to tell me stronger ionic bonds between the cations and anions. Don't waste a lot of time. Okay? Stronger ionic bonds than NaF. Finally, you must tell me what? You can tell me about the strength, but if you don't have the word energy, it's still not enough. Okay, so which requires more energy to overcome. Okay, concise enough. Once again, after all this is done, okay, go and highlight all the keywords. Okay, this sentence you must bring out whenever there are conflicting factors. Okay, lattice energy, strength, and energy. And this is I think, a more appropriate point, right? For me to tell you guys, what is the flow of your answer usually? Usually, guys, this is the flow. The flow, number one, you discuss the factor. So lattice energy is always about the factor, right? After the factor is discussed, the second thing is to tell me about strength. You tell me whether it's stronger or weaker bonds and all that stuff. Now, this is not just only in this lesson today. I will bring back this flow of answering towards the end of the chapter as well. And that one is more prominent. Okay, and then the third one over here is to link back to energy. Factor, strength, energy. Okay, try to follow this flow, and then your answer will never be too long one. Okay, all this is enough. Okay. Any issues so far? If you're okay with this, I need you to try another 2 more questions on the next page. Okay, no choice, I must keep writing on. Okay, you must write until you get tired of it. Okay, that's how you remember things like that. Okay, 2 more questions. Okay, give it a try. Write a full explanation. Perhaps what you can do, right, is to maybe follow what I do also. You try to play around with the arrows, the up arrow and the down arrow on the formula first. You play with it already, then you go write down the explanation. Then you have a peace of mind while writing. That's what I generally like to do. Right? Okay, play around with the formula first. Right, okay, so we have 2 more examples. Give it a shot. The first question, generally quite doable. Second question, a bit more tricky. You have to put an equal sign. This is wrong already. Yeah. If you all find yourself having to quote the formula in your answer, go ahead. But if it's an equal sign, they might penalize. So must be the ribbon, the proportional symbol. Okay. Okay, once you're done, I'll just write the answer on the board, and you'll get checked. Okay, take note, it's ionic bonds, not metallic bonds. I feel that for some reason, okay, some of us may write metallic bonds instead. Okay, let me just highlight a few things. Okay, again, acknowledge charge lah, because I know both of them is 2 plus charge, but don't just ignore it, acknowledge it first. Okay, then you tell me smaller ionic radius, then you can go straight to lattice energy. Good. Sorry. Okay, if you want to write the relationship in your answer, go ahead. You can write LE for short. And guys, you notice you do not need to write this statement here in this question, because are there any conflicting factors here? No, there's no conflict, so no point mentioning to me that charges are more significant. For what? Here the factor is ionic radius. Okay, so compare ionic radius instead. Okay, so yeah, ionic radius still plays a part. Okay, you tell me that this energy is larger. Factor, strength, energy, finish. Can I just repeat the same thing for part? And then we can move on swiftly from here. Okay, by now you should know the answering technique already. Okay, now it's just whether you know how to explain. Okay. Some of you may be a little bit caught off guard with what's happening here. Okay, no matter how hard you look, you cannot find the ionic radius of sulfate ion in the data booklet. Right? Okay, but who is definitely, but actually who's the smaller one? O2 minus, right? Does it make sense? Okay, because SO42 minus is a polyatomic ion, right? Okay, that's definitely multiple atoms. You're gonna have bigger ionic radius. Okay. Okay, sometimes, right, they can ask you to quote data from the data booklet. Later, maybe we can see some examples. So maybe for previous questions, if they ask you to quote data, you must quote the ionic radius. Like look at part 1. Part 1, the different thing is the ionic radius, the variable. Okay, but don't worry, for part 2, they won't ask you to quote anything because sulfate ion, you cannot find the ionic radius. Okay. Okay, so just finish up your answer for part 2. I'm not going to write that on the board. Okay, just take note, your answer should be MgO has the higher melting point. That's your conclusion. All right? Okay, as long as you stick to the factors, okay, you'll never go wrong for this segment. Okay, I'll wait for the rest to finish. Move on. Okay, so far, I don't think anything is difficult. Yeah, not yet. Definitely. Okay, so today's lesson, right, easy on the head, easy on our brains. Okay, it's just very particular in terms of how we present our answers. Okay, but concept-wise, really very simple. Okay, so we're gonna start to ramp things up, of course. Okay, because now ionic compounds pretty much finished already. Okay, maybe on the next page, there's like one more thing that I want to explain, and then we can end off ionic compounds as well. So I want you to take a look. The next page, okay, some basic stuff like ionic compounds cannot conduct electricity in the solid state. That one we definitely see before, right? Okay, you cannot conduct electricity because there are no mobile ions when they are in the solid state. Okay, it is fixed in position in the lattice. Okay, so that one very obvious. Only the molten and aqueous state, right? then it can conduct, because in that case, it is not rigidly held into place. Okay, there's some stuff that they won't really test all that often. You just need to know yourself. Okay, Ken? Okay, then after that, right, they mentioned something about brittle. Okay, compared to metallic compounds, right, metallic compounds get bent, but ionic compounds will just shatter. Okay, why is that so? Okay, we can present it in this manner again. A lattice is made out of a few layers. Okay, and guys, how are the ions arranged in each layer? Do you all know? Is it like plus, plus, minus, minus? Does that make sense? Okay, no, right? It should be alternating, correct? Because you need to make sure they're attracting each other. Okay, then can someone tell me what's the arrangement on the bottom layer? Okay, obviously minus, plus, minus, plus. Once again, it has to alternate in order for them to be attracting each other on all sides. Agree? Okay, so that's simple. But now, guys, you imagine the same scenario as before. I apply a force on the bottom layer. Now what's going to happen? They're no longer going to alternate, right? They're going to shift. And when they shift, they will reach a point where now the ions of like charges are beside each other. And when that happens, you can already guess what's going to happen next. They'll all repel at the same time. Okay, try not to use the word break in this case. Okay, break means it's like you crack something and then there's only one crack, right? But as you can see here, everything is repelling at the same time. So that means everything will die at the same time. That means the correct word to use over here is shatter. Okay, and that's why they use the word brittle and not fragile. Okay, so no, okay, there are very, very specific words in this chapter. Okay, but this is not that important. Once again, they don't really test this. Yeah. Okay, then with that said, yeah, I'm pretty much done with this portion, except for the last part. I'm going to talk a bit about the last part. Okay, good. Then nice. Okay, the last part, I just need you to highlight something. Okay, it says that ionic compounds are soluble in water. I'll only discuss that in the last lesson when I touch on solubility. But first of all, can you highlight ion dipole interactions? You have no idea what that means yet, never mind. Okay, I'll come back to that eventually. But for now, just highlight it. Now I just want to present to you guys a scenario. Okay, think about it logically. Okay, even though we haven't learned the actual concept yet, I'll show you guys this. NaCl. You all just tell me with your own general knowledge, can this guy dissolve in water? Can, because your table saw, right? You stir, it will dissolve. Okay, so NaCl and water can dissolve. Okay, sure. And it says that most ionic compounds are soluble in water. The keyword being most, because in science, right, there are always exceptions. Can you take this down? Al2O3 is an example of an ionic compound that is not soluble in water. Okay, this will not happen. And from whatever that we've learned today about ionic compounds, right, we can briefly make a smart guess, right, as to why this guy cannot dissolve. Even though we haven't learned what solubility is yet, right? Okay, let's just use a few common logical thinking here. Guys, ionic compounds, they have ionic bond strength. How do you measure the ionic bond strength? Using what? What's the idea? Ionic bond strength is using what to compare? Lattice energy. Good. Okay, so guys, we talked about lattice energy. Let's bring that back temporarily. Okay, we have this over here. Guys, let's make a comparison. Who do you think has the higher lattice energy between the two of them? Yeah, how do you know that? Okay, right, okay, you can already see it's very high charge, right? Okay, aluminium is +3, oxygen is -2. 3 times 2 gives you 6. Whereas for NaCl is +1 minus 1 is like ×1, right? So as you can already see, you don't even have to care about ionic radius. You already know Al2O3 has a way higher lattice energy. If Al2O3's lattice energy is much higher, what does that mean? Al2O3 has very what? Lattice energy only tells you one thing. Good. It tells you very strong. It's not just strong. All ionic bonds are pretty strong, but compared to NaCl, Al2O3 is super strong. And with this information in mind, can you all see why Al2O3 is insoluble in water? Do you think water, right, is strong enough to break apart Al2O3 and dissolve it? No. Okay, of course, the terms that I'm using right now are not accurate because we don't know what solubility really is yet. But common logic tells us that NaCl, lattice energy is much weaker. Water can dissolve it. But Al2O3 is just one of those super high lattice energies that cannot dissolve it. Can you see that? Okay, so that's the idea. Okay, water is not enough to break these strong ionic bonds. That's it. Let's move on. So that one we'll answer towards the last chapter, last portion, the last lesson of this chapter. Okay, for now, let's put it on the back further. Right? Any issues so far? Okay, so far, very good. Now we're going to move on to the most important class of compounds. Okay, so guys, move on to the next page. We're going to look at covalent structures, okay, covalent bonds. I will not be able to follow this structure very closely because it starts to deviate already. So take a look now, guys. I'm pretty sure you all know what covalent bonds are. In the notes, right, they also tell you the definition. And thankfully, guys, the definition you all don't really need to care. Okay, they tell you what attractions between nucleus and whatever, right? Okay, that one's not important. They never really ask. Okay, you don't need to write as well. Okay, but what we are more concerned with, right, is the fact that covalent bonds are all about sharing. Ionic bonds are all about what? Giving and taking, transferring of electrons, right? Okay, eventually, guys, okay, maybe I can talk a little bit about this. Ionic bonds is about transferring electrons. Covalent bonds is about sharing of electrons. These are two completely different ideas. We will eventually learn this thing called intermediate bonding in maybe the next lesson, as early as the next lesson, where we will then understand, right, that in real life, it's not as simple as black and white. There's no such thing as a completely covalent or completely ionic compound. In fact, everything is a mixture of two. So next lesson I will discuss. Okay, but anyways, covalent bonds are about sharing, yes. Okay, but let's answer a few fundamental questions. Okay, where can you find covalent bonds? Is it just in covalent compounds? No. Okay, so let's see. You can even find covalent bonds in ionic compounds. And since I've shown you guys a little bit of the dot and cross diagrams already, right? You all should have a rough idea of which kind of ionic compounds, right? Okay, we got CO3 2 minus. Okay, it can be SO4 2 minus or even PO4 3 minus. All these polyatomic ions are held by covalent bonds. And perhaps maybe you all can draw the structures inside as well. Okay, I've taught you guys how to draw the dot and cross. So you should actually know how to draw all these three compounds. But how do I know the shape of the compound, right? That one I will only be able to discuss in the next lesson. So you must draw it in these particular shapes. Maybe I don't need to draw PO4 3 minus. It's pretty much similar. Okay. Dot and cross, you all confirm can draw for all these three. Okay, with whatever I taught you all, right? Okay, confirm no one. Okay, it's just that these shapes we'll deal with in the next lesson. But anyways, okay, let's move on. The other one are called simple molecular structures. There's only one thing I want to discuss here. Okay, now of course the examples are very simple, like your hydrogen, chlorine, sulfur trioxide, shit like that without charges. Okay, this one everyone know, right? It's simple molecular. Okay, but I want you all to write this down. When it comes to simple molecular structures, and when we try to answer structure and bonding, I want you all to take a look now, okay? Just look up over at the board. When we say structure, yes, you can tell me simple molecular structure, but the bonding is very special. So I ask you all, just now, ionic lattice. The bonding is ionic bonds. Okay. Metallic lattice. The bonds is metallic bonds. But for simple molecular structure, you cannot tell me covalent bonds. Okay, very special. You cannot tell me covalent bonds. You must tell me about its intermolecular forces of attractions. Okay, let me just write IMFA for short. Now, take note of this here, because next time after you finish the whole chem bonding chapter, you'll be flipping all over the place. So might as well put it here first. I will not explain why yet. Okay, only when we touch on intermolecular forces, right? Then you see what's the significance of talking about this here. That means here the word bonding isn't very accurate, but never mind. Take note of this first. Okay, I'll come back to it in the third lesson. Okay. Anyways, okay, let's move on from here. There's another class of compounds which they have not mentioned over here. Okay, you tell me what class of compounds, right? Not mentioned here, right? Is also have covalent bonds. Think. So one more I haven't mentioned yet. Very good. Okay, simple molecular also have giant molecular. Now, to help us for the giant molecular is not taught in today's lesson. I'll only discuss it in the last lesson because it's in the last few pages of the notes. But for now, let me preempt you guys first. Can you list down all the possible giant molecular structures in our syllabus? Okay, guys, in O levels, you all learn some giant molecular structures. What are those? Good. Graphite, what else? Okay, good. Silicon dioxide, anything else? Okay, diamond. Okay, very good. Okay, so graphite and diamond, right? They are both allotropes of carbon. So you might want to express it this way: carbon bracket graphite, carbon bracket diamond. Okay, this is what we now express it as. Okay, there's actually one more. Okay, silicon dioxide, yes. Okay, but take note, guys, silicon. You pretty much only need to know these four. Of course, in exam, they can test a lot of random, never see before ones, but fundamentally need to know this first. Okay, then we'll come back to this in the last lesson. Okay, more focus on these two lah. Okay, because the first two you'll definitely see because common sense. Okay, the last two not so much. Okay, maybe as a way to help you all remember this, SiO2 is basically sand on the beach, like sand. Okay, take note. Oh, okay, thank you. Okay, so sand, right, is a giant molecular structure. You all know why? Okay, I ask you all. You all know molecules, right? From young, did they tell you molecules can you see using your naked eye? No, right? But can you see sand with your naked eye? One particle of sand? Yes, because one particle of sand, right, is one SiO2 molecule. It's that big because you can see it. Okay, so that's for your info, I guess. Yeah, so anyways, okay, let's just move on from here. Okay, with that all aside, okay, the next part, guys, very important. We're going to look at the different types of covalent bonds. Covalent bonds isn't called single bond, double bond anymore. Okay, here we're going to use names for them, very funky names. The first bond that I'm going to discuss is called the sigma bond. Now, sigma, don't spell the word sigma. You must know how to draw the sigma symbol. Okay, don't spell it out. What's the sigma bond? Now, I'm going to write this down in apostrophes because when I write anything down in apostrophes, right, it means that it's not entirely legit. It's just for you to remember only. Okay, this is the first bond. Yeah, I'll explain what this means. Okay, just take note first. Okay, right. I digress first. Guys, how are covalent bonds formed? Can you answer this question? Okay, write this down somewhere. How are covalent bonds formed? I know it's a very vague question, but you all just tell me. Any idea? How will you answer this question? Okay, very, very open-ended question. Can someone try? How are covalent bonds formed? That's very important. Okay, if you tell me covalent bonds are formed via sharing of electrons, you're not wrong. Okay, but we need to be a bit more specific. How are the electrons shared in the first place? Now, guys, you all have learned atomic structure. Can I ask you all, right, what holds electrons? I give you options. Quantum shell, subshell, or orbital. Which one holds electrons? Orbitals. Good. So guys, what's going to happen is this. Orbitals overlap to form covalent bonds. Later we'll look at some diagrams. What it means is this, guys. Orbitals overlap, and the region in which they overlap, right, is the place of electron sharing. I think it's better for me to draw a diagram, but you all just think of this first. Okay, I'll come back to this idea repeatedly. Okay, but you come back to the idea of sigma bonds. I need you all to take note. There's one bullet point that says this: head-on overlap. Okay, the orbitals must overlap head-on in order to call it a sigma bond. You must describe it as head-on. It's ultra important because, guys, sorry to break it to you guys, but there's chem bonding part 2 right in the middle of the year, and that one is a lot harder. Okay, yes. RI calls it chem bonding 2. Other schools call it something different. It's part of organic chem, basically. Okay, but you all need to know this. Okay, next. Let's look at some examples. So if you look back at the structures that I drew just now, right? Okay, this is called the sigma bond. And again, not single bond, sigma bond. Okay, this is called sigma bond also. Okay, good. Can I ask you, what's this bond called? Now don't look at it as a whole double bond. Look at it as 2 lines. The first bond is just called sigma. What's the second bond called? Later we'll come to it. But now just go and label your diagrams first. Okay, this is very important. Okay, so orbitals must overlap to form covalent bonds. Okay, have that idea echoing in your head. Can you tell me what are some orbitals that you have learned? What are the names of orbitals? Okay, how do you call orbitals? Is it like numbers like 1 or okay, no, right? Okay, it's s orbital, p orbitals. Okay, so we're gonna discuss the simpler orbitals. We also learn d orbitals, all the like dxy, all that nonsense, right? Okay, that one we won't discuss over here. Okay, in other words, you all can see from the notes, right? There are a few types of orbital overlaps. Okay, s orbital can overlap with s can overlap with p, and p can overlap with p. Okay, so we're going to draw this on the next page. Okay, it's written over there also. Okay, so let me show you guys some examples. Okay, perhaps maybe you all can try yourself. Okay, a little recap. S orbital what shape? Okay, good, spherical. You say sphere also can, I think it's fine. P is what? What's it called? Dumbbell. Okay, you must write that word. Okay, don't tell me infinity, don't tell me 8. Okay, no. Okay, dumbbell. Okay, go and give this a try. Okay, bear in mind, guys. Okay, bear in mind the word head on. Because different people have different interpretations of this word, so I'll let you all try first. Then later we draw the correct answer. Okay. You just draw a pencil because you never know. Okay, so quite accurate. Okay, some of you guys draw the axis, right? Okay, here don't need that. Okay, so let me just show you all. Okay, so Bell's one's quite close. Okay, S and S, right, is literally a Venn diagram. Okay, so S. Okay, what I need you all to do, shade the overlap and call this a sigma bond. Must label it. Yeah, okay. The overlap is where the two electrons in the bond come about. Then you see, one bond is 2 electrons, so the 2 electrons are here actually. Okay, next. S overlap with P literally just means this long. Okay, head on overlap with P, go and shade the overlap and label. Last but not least, P and P is the same thing now. Okay, P, shade, overlap. Later we look at more specific examples because some of you might ask me right now. Okay, when do I use SS? When do I use SP? When do I use PP? Later we discuss. Okay, when we look at the actual questions. Okay, but that's pretty much it. Okay. Alright, so all good. Okay, if all good, you look at the bottom of that page, bottom of the diagram. Okay, if there's a sigma bond, let me introduce another dude's name. His name is pi. Okay, pi bond, different type of overlap. Must highlight this one. Is a sideway overlap or side-on overlap. Both are fine. Sideway or side-on. Okay, so if you come back to the diagrams that we drew just now, right? Okay, pi bond in quotations are basically the second or the third bond. Again, never write this in exam, it's just for you to understand. Okay. The double bond is made up of a sigma and a pi, basically. Okay. So let me just go through. A double bond is made up of 1 sigma and 1 pi. Can I ask you, all right, what's a triple bond made up of? What's the first bond? Sigma. What's the second bond? What's the third bond? Pi also. Okay, so there's no like different guy name. Okay, it's just 1 sigma and 2 pi. Now this is important and it's very easy because they ask you this in exam. You just count. They give you one big structure, just count. Okay, cannot go wrong with this. Okay, can? Anyways, okay, what's more important here? You all look at the last bullet point. That is very, very crucial. When it comes to the orbital overlap, it's only PP overlap. Nothing else, like, don't have that many variations. So take a look. You can turn over to the next page and then just draw this in first. P is a dumbbell shape. So how a sideway overlap looks like, it's not like that. They're like kissing each other, right? No. Over here, it's really like sideways. Then the overlap is between like the sides. Let me mention some things. Sometimes in your school notes, you might see them literally overlapping sideways like that. Now this shit is just ugly and not practical because later when you give your examples, this one you cannot draw it. It's too messy. Okay? But anyways, I hope you all notice, right, that there are two overlaps, the top and the bottom. I'm gonna repeat. The top and the bottom is considered as one pi bond. Never ever do this. The top is 1 pi and the bottom is 1 pi. Never. Okay? To form one pi bond, you need two p orbitals to overlap sideways. You're gonna think of it as like chopsticks. Chopsticks is one set. Okay, that's just one set. It's basically one pi bond. Does that make sense? Okay, it's never pi on top, pi at the bottom. No. Okay, so just label one. Now, this is very important because later in the question, okay, I need you all to avoid this. Okay, so right now you all read the question. Okay, so leave a bit more space, okay, because we have a few more things to draw in this box. Okay. Now the question specifically says this. Okay, it says draw a PP side-on orbital overlap for a double bond and a triple bond. When they say PP side-on orbital overlap, just highlight that part. What are they referring to? Sigma or pi or both? Here is just pi. So guys, ignore the sigma bonds in the double and the triple bond. Okay, you must read the instructions carefully. If not, you do more than you are required. Okay, so look at this. Just right here. They only want you to draw. Okay, so we draw the double bond first. Double bond, I do not care about the sigma orbital overlap. Just draw the sigma here, and then now we move on to the pi. That's what we mean here. Okay, guys, how do you draw the pi? It's quite simple. Okay, so I just give you all this example. We have a p orbital here, p orbital here. They're going to overlap sideways on the top and the bottom. Just label one of them as the pi. Don't go and label both. Okay, this is simple. Because now I want you to follow this, right, and try the triple bond. Okay, this is for double bond. Now go and try triple bond. Again, triple bond, I don't care about sigma. So go and draw the sigma like this first. Okay, give you some time to try. The answer is very close. Why did you decide to put it crisscross? Any particular reason? Oh, okay, so it's just an aesthetic reason, right? Practical reason. Okay. Okay. Only see one pi bond, but then there's two pi bonds. Right, okay, so a little bit weird already, right? Okay, so first of all, okay, I use black first. Okay, let me color code this, I thought it gets a bit messy. Okay, so the first pi bond is the same as before. Now, I'm glad that I never see anyone label the top as another pi. Okay, clearly that's wrong. If you want to form another pi bond, you need another set of p orbitals. Agree? So how? Okay, should we do something like this? Now this will make sense, right? Because it's just another set that you just overlap. However, this is wrong, and I want you guys to take a look at how it actually looks like. I'm going to use red color so it doesn't look confusing. So if I want to do the same thing, right, for yourself. Now this is not diagonal, okay, because I need you all to imagine this. They are actually perpendicular to each other. Okay? The two p orbitals are perpendicular to each other. So I have one pi bond, black color, one pi bond, red color. Okay, I know from here you all see it looks like 45 degrees, right? But no, okay, I want you to imagine it this way. The black color and the red color like that, right? Facing inwards, but then it actually is perpendicular to each other. Okay, now there's a very important reason for this. And in the later half into J1, right, there's this thing called Chem bonding part 2, which is one of the most abstract topics. We will come back to this idea in that topic. But for now, just go and take note. The p orbitals must be perpendicular to each other. There's a reason for this. If you watch your first part of atomic structure, you will know also. Can I ask you all, right? How many p orbitals are there? 3. What are the 3? And what do the x, y, and z represent? The axis. Guys, the axis, they are all perpendicular. 3 dimensions, all perpendicular to each other. So there's no way I do not want to see 2 p orbitals on the same axis. Doesn't make sense. If there's one on the x, the other one must be on the y. If there's one on the z, then must be one on the x, something like this. Okay, can? Just a menial reason, so it's just when you draw. Okay, again, this one's quite challenging, but you never know, maybe your school will test. Okay. Right, very nice. Okay, so let's take a look at the next bond. Right, then maybe after the next bond, right, then after we do one question, we can take a short break. Okay, if not, there's a lot. Okay, so one more thing left. Okay, then we take a short break. Okay, we take a look at dative bonds. I've already taught you guys what dative bonds are in the dot and cross diagram segment. Okay, so there's not much for me to discuss anyway. Okay, I just want to discuss the explanation for dative bonds. Okay, so I already told you guys dative bonds is a subset of covalent bonds. Covalent bonds is about you give me one, I give you one. Very fair contribution. But then dative bonds is I give you 2. We give 2 each. Okay, we are sharing 2. Right? Okay, that's the idea. Okay, I told you guys already. Okay, but the idea is that for dative bonds to occur, there are some criteria to fulfill. Okay, there must be someone to give and someone to accept. Right? It's not a 1-1 situation, it's a 2-0 situation. So it's a giver and there's a taker. Okay, it's a donor and acceptor. Make sense? Okay, what must a donor atom have? If you all recall from all the dot and cross diagrams that we drew, all of them must have a lone pair of electrons. Guys, what's the definition of a lone pair? Please take note. This one will really help you all understand this better. A lone pair is a pair of electrons that are not involved in bonding. That's why they are extra, they're just sitting there, right? Since they are not involved in bonding, they are not doing anything useful, right? Why not just give it to the acceptor atom? So the acceptor atom, what must it have? Okay, it must have a vacant. You guys, let's fill in the blanks. Vacant quantum shell, vacant subshell, or vacant orbital. Which one is the thing that can accept electrons? Orbital. Once again, orbital is the smallest unit that holds electrons, right? So it's a vacant orbital to accept a lone pair of electrons. Once again, guys, orbital can hold how many electrons? 2. No matter what kind of orbital, max 2 only. Just nice, a lone pair is 2 electrons. So everything fits together nicely. Okay, good. So if you want to answer your question, it's just basically this. We're just going to look at an example. Okay, so can you all take a look at, flip a few pages. I want you to flip all the way to page 16 and look at question 3. We're just going to use this example to do this question. Okay, good. Okay, so draw the dative bond in that compound, NH3BF3. I'm pretty sure you all can guess. NH3BF3, if you separate them, is NH3 and then BF3. Right, okay, so perhaps since you all learned dot and cross already, okay, you all going to draw the structures of NH3 and BF3 first. Draw the dot and cross, sorry. Okay, NH3 and BF3. Okay, just a little short dot and cross exercise here. Okay. What? Monkeys. Okay, now that we have some context, right? I need you guys to also identify who is the donor and who is the acceptor atom. I think it's quite obvious after you have your dot and cross diagram out. Okay, so if you're still struggling a bit with your dot and cross, right? I suggest go back and look through it first before the next lesson. Because next lesson I'm just going to go straight into dot and cross. Okay, so generally you all should get this structure. Now, N has how many valence? 5, right? Out of the 5, how many are used for bonding? 3. Because 3 bonds each. So we are left with 2. The 2 is basically your lone pair. Now they can ask you to draw this in exam. It's just that this particular question they never ask you. Okay, but the tutorial I think they have. Okay, and then afterwards, right, I'm pretty sure you all can see BF3. Put closer. BF3 looks like that. Fluorine has a bond each, but boron only has 3 valence. So 3 valence, 3 bonds, no lone pairs. And what do you all notice? Okay, who is the donor atom in this case? The donor atom is nitrogen, right? Yeah, it has a lone pair. Who is the one that's accepting the lone pair? Can you see boron? Because boron in this case, you're going to count as a total of only 6 valence electrons. He can still accept another 2 more because octet rule is 8 valence, right? So here, vacant orbital is in boron because boron only have 6 valence electrons even after bonding. So go and write this down. Sorry, not 6 valence. Yes, 6 valence after bonding. So you can still hold another 2 more, which is exactly 1 orbital. Okay, now how do you draw the diagram? I need you all to be very careful with this. Okay, this is the wrong diagram if you draw like that. Okay, because some of you guys, right? Okay, the dative bond I show you already is an arrow. Nitrogen is giving to boron, yes. But I over here see 2 things. I see a dative bond and a lone pair. How many electrons are there over here if you draw a lone pair and a dative bond? 4, right? Okay, you can all see it's a lone pair plus another 2 more, which is not true, because you are just putting the lone pair over here. Do not draw an arrow in this case. This is still dot and cross. So I need to see 2 dots. 2 dots giving to the boron. So this is the full structure of NH3BF3. So that's how dative bonds work. You guys already know how it works. Okay, then they ask you to explain how it's able to form a dative bond, right? It's basically this, but with context. Okay, so what do I mean? Okay, there is a lone pair of electrons on nitrogen, right? The lone pair of electrons on nitrogen in NH3. So I am very specifically referring to this context. Okay, the lone pair of electrons donates into the vacant orbital of boron in the BF3. So you're just regurgitating the definition of the criteria, but with context. Okay? If you just tell me lone pair donate into vacant orbital, they'll just ask you who, where. Okay, so that's pretty much. Okay, if you want also, right? Okay, if you don't, other than the dot and cross diagram, once we learn all the shapes in BSEPR theory, okay, then the diagram will look slightly different. The diagram will look something like this. It's a lot more polished. Okay, so you all can draw this in as well. There's an arrow. Let's draw this in as well. Okay, all good? So 3 types of covalent bonds. Okay, so far I never thought about strength yet. Factors affecting strength. Okay, I only thought about the different types. Okay, sigma, pi, and dative. Okay, good. All right, we take a short break first. Okay, go toilet or whatever. Okay, then we come back in about 7, 8 minutes. Okay, take a longer break. Okay. Okay, if anything I ask, you can ask me now also. Okay, so yeah, page 15, some orbital questions they need to draw, right? Okay, show the overlaps and all that. But now we have context. Okay, so they tell you it's hydrogen or whatever, right? Okay, you're gonna try for the first 2 parts first. Okay, part 3 is a little bit more that you need to draw. You see whether you understand your orbital overlaps. Yeah, your hydrogen can put inside the orbital. Yeah, because you can technically count it as hydrogen as the center of the atom itself. Yeah. Okay, part 1, most of you guys got it. You shade it in the table. Hey guys, just now sigma bond got a few variations, right? It can be SP, SS, PP. Okay, which one must we use over here? Is there a must or you can just draw anything? Okay, why must we draw SS? Yeah, okay, because it's hydrogen, right? Okay, hydrogen only have one S1, no p orbital, so it's wrong if you draw a p orbital. Okay, here, right, you can put the hydrogen in the inside, okay, to kind of give a bit of context. Remember the way shade and label. All right. I think part 2 is also equally simple, but not much. Okay, it's the same thing as what I mentioned. Part 2, they only want the pi bond in the double bond. So that means you can ignore the sigma bond. Just call that sigma. And then the orbital overlaps. Yep. Okay, give part 3 a try, because if you all read the question carefully, they want you to draw the orbital overlaps of not sigma, not pi, but the entire double bond. So you need to have both orbital overlaps for sigma and pi. Okay, there are multiple answers here. You all can go and try whatever you think is correct. Okay. The whole the whole double bond in part 3. Okay, now it's just a double bond, a CO double bond. Don't go and give me the other side because later I'll explain why. Okay, carbon dioxide is a bit interesting. Just give a bit more information here.
both of these are pi bonds. Now remember, a double bond is a sigma and a pi. So sigma must be head-on overlap. But then over here, right, it's 1 sigma 2 pi, which is a triple bond. That's only a double bond. Yes, you don't need it. It's too much. Yeah. Okay, and the sigma bond, you cannot just draw a line because they want you to draw the orbital overlap of both the sigma and the pi. Okay, so guys, let's take a look. There are some possible answers here. Okay, so one answer that you guys have drawn is the sigma, you just draw 2 s orbitals overlapping. Now that's good, that's not wrong. Okay, and in other words, the pi bond is the sideway overlap of the p orbitals. Okay, fine, that's correct also, just make sure you label. Okay, but there are other variations, and eventually we're not going to draw this variation as we learn more about chem bonding. Okay, I will show you all the more appropriate variation here. And because carbon dioxide looks like this, let me just give you guys a bit more idea on what is going on in the entire carbon dioxide molecule. I know this question only asks you all for the CO double bond, but what if you have the other double bond as well? Okay, so we position it properly first. Carbon and oxygen, instead of SS orbital overlap, head-on, is there anything we can do also? Anything else? Can we do PP head-on orbital overlap? Can also, right? Because carbon and oxygen have p orbitals. Your 1s2, 2s2, and all that. Okay, so I can do something like this. So if you're wondering how a p orbital looks like, right, it's just like that. I know a p orbital is made out of 2 lobes, right? Okay, so hold on for a moment first. Okay. Anyways, okay, you can draw the other side like that. You can draw a bit smaller because it's not the key point over here. All right, next. The pi bond is just like that. Okay, so everything here is fine so far. If you draw this diagram, it is okay as well. PP head-on orbital overlap and PP side-on overlap. Now, when you all learn the future of chem bonding, right? Yeah, okay, this is no longer just a p orbital. Okay, it's a different thing altogether. But I don't want to confuse you all of anything yet. You all just learn whatever we learned here today. Okay, but anyways, guys. For the sake of me drawing the other oxygen on the other side, okay, just pay attention, I'll just look at the board first. Okay, I will show you guys how it's actually done on the other side. Okay, then I need you all to kind of discuss together. Okay, CO, the other side is oxygen also, right? Okay, the sigma bond, also another sigma, right? Let me just draw the sigma bond first. Okay, so that's fine, that's not what I want to discuss. Can you possibly draw can you draw the pi bond? Okay, go and try. That's just the other side, I'll just go and fill it up. Okay, so I'm drawing for the entire carbon dioxide, by the way. They are still blur, right? This is sigma, this is sigma. This is also pi. I just want you all to draw this other pi on the left-hand side. Okay. Okay, see a few answers. Okay, I see some correct, I see some wrong answers. Okay, so it's kind of split up. Okay, guys, see some of you drawing this, and then you label, you shade like that. Is this correct or wrong? Correct, right? Eh? Another pi bond. Okay, but you can't do this because as I mentioned, guys, if you want another pi bond, you need another set, right? You can't share this guy. This guy is taken already. Okay, this guy cannot 2 times, okay, it doesn't work. So what's gonna happen is this, guys. Okay, some of you got the correct answer. Very good. Over here, right, if you want another pi bond on this side, I need to see the perpendicular version. So if you look at the carbon in the center, right, it actually has 2 of these p orbitals being used for pi bonds. I color code it so it's less messy. Now, we will further explain why carbon here has 2 p orbitals, even though it doesn't have a triple bond. Okay, only in the second half of chem bonding, later in J1. Okay? It's under this topic called Intro to Organic Chem for some of you guys, but for RI, right, they call it Chem Bonding Part 2. Okay, that's why orbital overlaps can be quite intense. Okay, but for now, I tell you in advance first. Okay, you just need another set. That's all you need to know here. You just need another set. And the set cannot be parallel as well. The guy in the middle cannot 2 times. So you give him another set. Okay, Ken? Alright, okay, so with that out of the way, can you all just look at question 2. We discussed question 2 together, and it allows us to transition into the next and last portion for today. Okay, take a look. Sigma or pi, which one is stronger? Okay, we never talk about strength yet. Okay, it's the factors affecting strength. Sigma or pi, which one do you all think is stronger? Any guesses? Okay, why will you say sigma? You must justify. Yeah, why say sigma? Why are you so confident in saying sigma? Come, let me hear you guys out. Any idea? Closer to the nucleus. Okay, similar idea, but not there yet. Okay, quite close. Okay, but I need you all to come back to this question again. How are covalent bonds formed? What's the answer to this question? Okay, guys. Covalent bonds are formed via orbital overlaps. So can I now ask you all another modified question? The strength of a covalent bond depends on how much it overlaps, right? Okay, if the orbitals overlap more, is it stronger or weaker? Stronger. And overlap less is weaker. That's it. So guys, here, okay, if you're talking about strength, it's basically extent of orbital overlap. So in this case, sigma or pi, which one is stronger? Okay, why is sigma stronger? Okay, good. Because the word there is head-on overlap. Okay, think about it this way. Head-on, why is it better than sideways? It's like when you go out on a date with a guy or something. Okay, if you want to hold his hand, right, that means you all got chemistry, right? Quite strong. You all like each other. Okay, but if let's say you go out on a date with this guy and it's a bit weird. Okay, will you want to hold hands with him? Probably not, right? Okay, you probably just don't want to hold his hand, then you're walking that time, right, side by side. Okay, but you don't dare to hold each other's hand. Okay, so that's the idea. Which one is stronger? Definitely when you hold the guy's hand, right? Which is your sigma bond. To explain this, I need you to write this down now. Okay, your sigma bond is head-on overlap. Yes, you list down whatever first. Whereas your pi is side-on overlap. And because of that, you all can tell me that head-on overlap is more effective. Okay, the word here is effective. Okay, so we are not really using the word extend, more effective. Okay, so that's why sigma is stronger than pi. Okay, done. And this will bring us to the next portion on strength. Okay, turn over to the next page. Now they have answered this. So we're going to discuss the strength of covalent bonds. What factors affect them? Now, guys, if you turn over to page 17, don't be confused by the formatting. I just want you all to maybe write this down yourself. Okay? Bond strength depends on basically what we just mentioned. Effectiveness of orbital overlap. Or basically the extent of orbital overlap. This is the key idea. There's no 1, 2, 3. The 1, 2, 3 doesn't mean 3 separate factors. They're just like points. Maybe the formatting a bit bad. Okay, maybe I need to change it. Okay, but anyways, just this. Because I already told you all why. You already understand why. Now, what does effectiveness of orbital overlap depend on? Because sometimes we are given 2 different bonds, right? Okay, we do not know what is better or worse. Okay, so let's take a look. Okay, now effectiveness of orbital overlap actually depends on the atomic radius. Basically, the size of the atom. So let me ask you all, larger atoms, do you think they overlap better or worse? Okay, overlap more or less? On the other hand, smaller atoms, do they overlap more or less? Okay, so I ask you, larger atoms, do you think it overlap more or worse? Or more or less? Okay, actually it's less. Okay, so I know this is a slightly counterintuitive idea. Larger atoms overlap less, but smaller atoms actually overlap more. I know it's a bit counterintuitive. Come, let's explain. Okay?
Okay, we're gonna draw a little diagram here to help us see why. Okay, so CF versus CI. Okay, first of all, can you tell me who is larger? Okay, just always go ahead and check who is larger. Okay, I, right? The I atom. We don't care about C, C is the same. Okay, I is larger. So how does this work? If you were to draw the orbital overlaps, right? Okay, CF is like pretty decent. Okay. So you have overlap here, okay, sure. But CI will basically look like this. C is the same, but I is massive. And I need you all to take a look. The logic is you can look at it this way. This overlap, right, is maybe about 20% of the entire F size. Okay, but this one, right, the percentage is larger or smaller. It's way smaller of iodine, right? So maybe only like 2%, for example. That's the way you can process this. Again, yeah, you don't need to go into detail, just tell me this can. Yeah, so in case you forget, please take note of this. Alright, so with that said, all I need you all to do is to answer the question on page 18. That's it. Yeah, okay? Okay, if I want to see all your keywords and all that, okay, I pretty much told you all what's required already. Okay, so they're asking about HCl and or HBr. Okay, what's the first point to compare? Okay, if we're talking about CL is larger or smaller than Br. Okay, smaller. So don't just say smaller. CL has a smaller atomic radius than Br, make it more professional. Okay, and because of that what? HCl has a more effective orbital overlap than HBr. Okay, finally, what does this mean? Which bond is stronger? Yeah, of course, HCl. Okay, HCl is stronger than HBr. Now, this portion here is like ultra easy for all of you guys. Okay, but then right, not so much when I finish the topic. Okay, because the moment at the point I finish the topic, there'll be so many concepts, right? That I will mention this at the end of this chapter again. Because there will be something, right, that will confuse you guys when it comes to bond strength. Okay, so for now, it's fine. Okay, and this is the thing over here. Let me just expand on it a little bit more. Okay, before I do something to end off the lesson. Okay, we're gonna talk about bond length. Okay, so we talk about strength, right?
Okay, bond length also depends on this effectiveness of orbital overlap. Okay, so to add on as bond strength and length. So I know the notes put there like kind of separately, but no, it's the same thing. Guys, if the overlap is more effective, is the bond longer or shorter? Just visualize in your head. If the overlap is more effective, longer or shorter? No, it's shorter, right? The more you overlap, can you see my hands getting shorter? The less you overlap, the door open and door close scenario, longer and shorter, that's it. Yeah, okay? So stronger bonds tend to be shorter, weaker bonds tend to be longer. It's just a relationship, okay? Nothing much here. Okay, and then the third point, we really don't have to discuss, that one common sense, right? Triple bond stronger than single, double bond stronger than single bond. Okay, that's not important. Okay, so they can ask for length, they can ask for strength. Again, guys, fundamentally, right, it's always about effectiveness. You must mention that. It's a must. Okay. So the formatting in the notes, I apologize for that. Okay, but it's basically just this idea. Okay, anyways, guys, okay, to end off the lesson, right? Okay, let's just do. Yeah, I was looking at some tutorial question, but I'll try to make it a bit more difficult. Okay, the tutorial too easy. Can you all look at this structure here? Okay, what I need you all to do is to tell me how many sigma and how many pi bonds there are. Yeah, go ahead. Okay, just go ahead and draw this somewhere and then just label this, I guess. Okay, it's basically question 3 in the tutorial. But I know some of you guys, I might not have given you guys a tutorial yet. Okay, so just draw this. Okay, tutorial I only use at the end, so now we do have it, it's okay. Right? Common MCQ question. Okay, just tell me how many sigma and how many pi, and we are done for today. No, just count the number of sigma. If I don't need draw that one will take too long. Yeah, just count how many, just tell me the numbers. Yeah. Okay, as you go on into JC, right? As you go on into organic chem, especially because it's an organic molecule. Okay, organic chem is very huge, sometimes the molecule. So then they will just ask you to count the number of sigma and pi. It's not even the worst. I've seen some where you count for like 25 sigma bonds, like the thing that huge have. Yeah, every not joking. Okay, that one a bit too much. Okay, like count then you slip of mind, right? Then you count wrongly, then yeah, okay. So anyways, okay, we just do this first. Okay, guys, how many sigma bonds are there? Is it 8? Then 1, 2, 3, 4, 5, 6, 7, 8. Yeah, correct? Okay, no, answer is 11. Okay, why? Don't forget here. Okay, they always like to hide the bonds. Okay, take note. They love doing this. Okay, they love hiding this shit. It's a bit annoying. Okay, so never forget the CH3. CH3 itself, if you go expand it yourself, there are 3 sigma bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, it's not even 11. The answer is 12. Count wrongly. Okay, my bad. Answer is 12. Okay, why 12? Okay, guys, I think maybe, perhaps even I also just now forgot that CN was the bond here. CN. If I draw the bond, what do you think is this bond over here? No, it's a triple bond. You notice nitrogen must hold 3 bonds, carbon must have 4 bonds. So this is a triple bond. They love hiding it. I know you all haven't learned CN yet. Okay, but sometimes you all must see, they can pass on. Okay, CH3 they can expand. So let me just draw everything out. To expand this, CH3 looks like that. So go and count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many pi bonds are there? 3. 1 here, 2 here, 3. Normally, guys, the number of pi bonds are very easy to spot. So you should count pi bonds first. Sometimes MCQ, you know how to eliminate bonds. Okay, so that's how a question like this will work. And that's how people can get this wrong, even though it looks very simple. Yeah, okay, so yeah, that's it. That's it for today. Okay, so today is just content heavy, not difficult. But following up is gonna get more challenging. Okay, so anyways, before next lesson, we'll touch on BS EPR theory. So please have a little bit more, you're going to look through your dot and cross again. You might want to redo the questions that I show you guys in the, when I saw you guys separately. Yeah, okay? And that's it for today. Okay.